Hello everyone, I'm Bingyu, a PhD student from Peking University. Today I will present our work, Grouptuner Efficient Group-Aware Compiler Auto-Tuning. Compilers provide hundreds of optimization options for users to improve program performance, but the huge number of options and their complex interactions make it difficult for users to fully understand and leverage them. And improper use of options may even degrade program performance. As a result, compilers provide standard optimization levels such as O3, a fixed sequence of options, and can improve performance in general. However, as program features and hardware architectures varies, standard optimization level cannot always guarantee the best performance. For example, the figure shows the performance improvement percent over O3 after random auto-tuning, and the maximum improvement can exceed 30%. This means that we can find sequences performing better than O3, and this is why we need compiler auto-tuning. Compiler auto-tuning can automatically identify better option sequences for specific programs. This figure below shows the auto-tuning process. The search algorithm begins by generating option sequences and evaluating their performance. And guided by the observed performance differences, the search algorithm iteratively refines its search direction, progressively generating and evaluating new sequences until converging to near optimal sequences. And the key to auto-tuning is to identify critical options that significantly impact program performance, and then focus the search on these critical options to improve searching efficiency. For example, BOCA identifies critical options based on Bayesian optimization and random forest model, and the CFSCA identifies critical options based on program structures and flipping strategy. However, the biggest limitation of the existing solution is that it cannot accurately identify critical options. This is because the search space is sparse and noisy. Existing masses typically change multiple option states across the entire search space in each iteration. As a result, iteration history often contains sequences differing in the states of many options, and there are many redundant options that do not contribute to the performance, making it challenging for algorithms to accurately determine which specific option contribute to the performance improvements. For example, in the following iteration history, these two sequences differ in the states of three options, but in fact, only one option contributes to the performance improvement, and the other two options are redundant, and the program do not have the optimization space for them, such as the option targets at the switch statement to optimize the option that contains no switch statement at all. Moreover, these truly critical options do not independently improve program performance, and it relies on the interactions with other options whose states remain unchanged between iterations, further complicating the algorithm's ability to correctly recognize its importance. As a result, algorithms often mistakenly regard all differing options as potentially critical and subsequently prioritize these options in future searches. Such inaccurate identification of critical options leads to the generation of suboptimal new sequences and ultimately reduce the overall search efficiency. So how should we identify critical options? Our insight is rather than inferring critical options from limited history data in sparse and noisy search space, we directly leverage historically high-performing sequences as a start point in each iteration. As the evaluated high-performance sequences in early iterations have demonstrated their potential effectiveness, they offer a solid baseline from which local adjustments can uncover gains. And since blindly modifying the states of all options across entire search space risks destroying its existing interactions between options and causing performance regressions, we adopt a more controlled approach, restricting the modification of each iteration to a small functionally related group of options, and this preserves the original high-performance structure of the evaluated sequences and can further explore the new potential critical options and interactions. For the same iteration history we showed earlier, Grouptuner directly selects the better performing sequences as a new starting point and only mutates the states of one functionally related options or group of options, for example, loop options, without explicitly identifying critical options. It explores new critical options while preserving the states of previously effective ones, even if the algorithm mistakenly alerts the states of critical options. The worst sequences will be discarded in the future, and the search will then continue based on the prior high-performing sequences, ensuring that the overall search direction remains unaffected. Next, we introduce the overall structure of Grouptuner, which consists of two main stages, option grouping and the group-aware mutation search. In the option grouping stage, we organize the options into functionally related groups, and then during group-aware mutation search, Grouptuner performs mutations at the group level based on historically top-performing sequences. The goal of grouping option is to partition the search space to functionally related groups to facilitate the group-aware tuning. Based on the GCC completion process, we can group options according to their relationships with passes. Specifically, options that control the same path or are associated with the same stage can be grouped together. It is because the paths with the same stage usually share similar goals, and options invoked by the same path have higher probability of exhibiting synergistic effects. Specifically, option grouping has three steps. First, we group options that belong to the same path, and then we merge overlapping groups as certain optimizations span multiple paths. Finally, we assign ungrouped options, those linked to isolated paths, to the nearest existing group based on the path execution order to avoid over-fragmenting the space. And this grouping strategy can facilitate the discovery of synergistic effects among related options during the tuning process, thereby improving the overall program performance. Finally, we categorize 200 GCC options into 15 functionally related options, and each group contains 4 to 28 options. And then we design group-aware mutation search process based on the option grouping results. And the core of the group-aware mutation is how Grouptuner generates new sequences based on iteration history. We first select a top-ranked observed sequence from the iteration history and randomly select one group, mutate the states of the option within the group to generate the new sequence. At last, we can retain original high-performance structure and effectively explore potentially new critical options and their synergistic interaction. And our auto-tuning process includes two steps. First, initialization. We use the O3 configuration as the initial start point, as it represents an effective and well-established optimization sequence crafted by compiler experts, and to avoid getting trapped in local optima by relying solely on the best performing sequence from previous iterations. We perform multiple group-aware mutations on the O3 sequence to generate and evaluate diverse new sequences and add them to a candidate list, serving as start point for the subsequent iterations. Second, we perform history-based search in each iteration. We randomly select one sequence from the candidate list and perform group-aware mutation on it to generate a new sequence. After measuring its performance, If the new sequence outperforms the worst sequence in the candidate list, it directly replaces it. Otherwise, we apply the simulated annealing strategy to decide whether to accept the new sequence, and which helps maintain a balance between the exploration and exploitation and avoids premature convergence. We evaluate the effectiveness of Grouptuner using GCC9 as the target compiler and set the number of iterations to 500. And our benchmark suite includes programs from Cbench, Polybench, and Spec. The right figure provides the detailed information about the benchmark. And we compare Grouptuner with 5 approaches: random iterative algorithm, simulated annealing, self-SCA, BOCA, and SR-tuner, which the later 3 represent the latest state-of-art auto-tuning algorithms. And our evaluation metric is the percentage improvement in performance over all 3. First, we evaluate the performance improvement achieved by Grouptuner. The figure on the right shows the average performance improvement over all 3 for each algorithm on the benchmark set and measured by every 50 iterations. We can note that within 500 Turing iterations, Grouptuner gets the highest overall performance improvement at 12.38% over O3, up to 3% better than others. And we can note that Grouptuner consistently maintains the highest performance throughout the entire tuning process. Next, we analyze why Grouptuner can discover better sequences more efficiently than existing methods. The figure on the right compares the performance trend of sequences over iterations for Grouptuner and BOCA. We can note that the average performance of sequences generated by Grouptuner is better than BOCA, and there are 3 main reasons why Grouptuner can be better. First, it fully makes use of iteration history. Grouptuner generates new sequences based on top-ranked evaluated sequences, enabling the search to build on past successes. Second, Grouptuner enhances discovery of better sequences by group-level mutation, increase the likelihood of uncovering new critical options and their synergistic relationships. Third, Grouptuner has better search stability. Although occasional performance drops may occur, Grouptuner discards suboptimal sequences early, only choose the top-ranked evaluated sequences as a start point, preventing the suboptimal sequences from hindering the overall optimization trend. Next, we evaluate the search efficiency of Grouptuner. We compare the total time consumed for 500 iterations for each algorithm and define the efficiency as a time ratio relative to random iterative algorithm. The figure shows the efficiency of different algorithms, and we can note that the Grouptuner is the fastest algorithm, consuming only 77% of the runtime required by random iterative algorithm. Conversely, methods such as the FCA and BOCA, which retrain prediction models using updated historical data in each iteration, exhibit significantly higher overheads, and this prohibitive tuning overhead severely limits their usability. And we also evaluate the performance of Grouptuner on other GCC versions, such as GCC11 and 13. The results show that Grouptuner can still achieve better performance, demonstrating its effectiveness. In conclusion, we propose Grouptuner, a group-aware auto-tuning algorithm that functions the search at the group level. And the Grouptuner can achieve the best performance improvement compared to SOTA methods with an average speed of 12.39% over O3, and it is also the most efficient, requiring only 77% of the time required by random search algorithm. And this is all for our representation. Thanks for listening. We are happy to take any questions.
Okay, let's give it for Bingyu first. And please raise your hand if you have any question or comment. Yes.
Thank you for a great talk. Actually, I was an author of the SR tuner. Actually, I was so sad for that the SR tuner shows the lowest performance in the evaluation. But anyway, it is a really good job. My question here is that your work looks really good, but do you think if this work achieves the theoretical maximum performance, or close to that, or if not, which opportunity do you miss?
Sorry, can you?
Oh, my question is that, what do you think about your performance gain now? Is it close to the maximum or not? Is it still far from the maximum performance we can get?
Actually, we may never know the maximum performance improvement because the search space is too big, too huge. Yeah. But actually, we do experiment with longer iterations, such as our evaluation is 500 iterations, and we test 1,000 iterations further, and the improvement can be higher. Yeah. So if we have enough computational resources, the performance improvement may be higher. So it still has a gap between the maximum performance improvement. Thank you.
Is there any other question or comment? Actually, I have a question. So you show the list of the group, and is there any automated methodology to group these things?
Actually, it's a difficult problem, and it is because the completion process of GCC is complicated, and it have been updated over years, and the completion process is complex, and we do not have a clean and beautiful strategy to automatically group them. But we have tried our best to find their commons, and we find that the options within the same path has the higher probability to have the close relationships. So that is our solutions.
Okay, thank you for your answer. Is there any other question? Actually, I have a follow-up question, so if I can spend more time, then I have one question. So you show like the great experimental result, and you explain why your work outperforms like Professor Park's works, SR Tuner, and you beat him. Actually, my question is, depending on the target processor, your like auto-tuning methodology shows the variety in performance. Have you observed that phenomenon, or can you explain further about your the performance variability in depending on the target performance?
About why it is better?
Or like, is it working on like the different type of the processor? That's my question.
We just evaluation it on the LCTES'25 processor. Yes, it's our computational.
Okay. I'm not rushing or giving you some pressure, because like nowadays China is developing a lot of CPUs and processors. So I'm just asking if you have some more experimental results on with the processor in like the manufacturer in China. That's the thing. Yeah.
No, we do not evaluate it on other CPUs, and it because the experiment is quite time consuming.
Yes.
Yes, it makes consumed over 1 week to complete the work. Yeah.
Okay, this is a really great work, and thank you for your presentation. And once again, let's give it for Mingyu.